Hey, it's Ivan from the EV Stock Channel here, and welcome back to another episode in which we're going to look at Tesla's battery raw material supply chain. In today's episode, we're going to map out Tesla's lithium supply chain. Now, I'm no expert in this field, but I've come across someone who is. Rodney Hooper will be on the show, so without further ado, let's jump straight into things. So Rodney, do we have an arms race going on in the battery raw material space? If it takes 3 times longer to get a mine up and running compared to a battery factory, doesn't mean that it's game over for anyone that shows up late to this party.
Unfortunately, electric vehicles are a disruptive technology as a concept. But unfortunately, the materials that go into an electric vehicle are very much rooted in mining. The other thing, of course, as well, is if you look at the metals and materials needed for an EV, they are different from what's needed in an internal combustion engine. So you are asking a supply chain to redirect itself. And if you look at the time horizons of what it takes to permit, to construct, to commission, to ramp up, and to meet battery quality criteria, you're looking at 5 to 7 years.
Wow.
This is the thing that we've been trying to explain in the industry, and I'll talk about the separate pricing, but it is of a concern because if you see massive demand as EV adoption is going to grow in the next couple of years, and that's driven by battery prices dropping, and that's, I guess, what we're all waiting for Tesla to come with a wow factor in the sub $100 kilowatt hour batteries to make EVs on almost any metric cheaper than internal combustion engine, is all disruptive technologies have a exponential growth chart once they kick in, the hockey stick, whatever you want to call it, that massive growth. iPhones, anything in your past, cell phones. The thing is, though, is that what it takes, the amount of lithium it takes to put in an LCO battery in your phone is not a material issue. It's a few grams. But what's needed in a car is something very different.
So how much lithium would be in a car, for example? Like, what would be the weight? If you took a standard Tesla vehicle, how many pounds?
It's linked to a kilowatt hour, and I don't want to, because the technical guys, will be up in arms. So what's in an actual cell when you strip us, when Sandy Munro or someone strips down a Tesla, what you see is the weight in the cell is the final product, but there are production losses and certain slippages that happen in the production process from cathode to cell, and going into pack and so on. So roughly speaking, we work off 0.8 kilos per kilowatt hour. So if you have a 50 kilowatt hour Model 3, you roughly, if you take all of the losses and everything else and include that with what's in the cell, and bear in mind, you've also got to include, let's say, faulty cells that have been thrown out, batteries that have, there's been the rare degradation and a battery pack has to be replaced. So I'm saying, roughly speaking, over the whole industry, we work on about 0.8, and I would say that's a fair rough estimate for Tesla. So 50 kilowatt hours, 40 kilos. That's your number.
Wow. Okay. No, that's...
And bigger the pack, more lithium.
Okay.
So just to get back on our earlier topic. So Tony Sieber, I love. I don't know if you've seen his stuff on disruption and technologies. And he made a comment a few years ago, and someone retweeted it with their own comment about how all of the cars sold in 2025 will be EVs. Now, the problem is, this isn't Airbnb or Uber, where there's a few programmers sitting in a room. In order for every car sold in 2025, and let's assume there's 90 million cars sold per year, the lithium that would be required, and the nickel and the cobalt and everything else for every car to be an EV, unless we all shifted to plug-in hybrids, which I just don't see, because things like Tesla and other competitors are making phenomenal full battery electric vehicles. It is not possible to see that happen, because just as I've said to you how long it takes to start a lithium mine, if you cut me a check today, this afternoon, and said to me, go and build the mine. I could not permit it, build it, ramp it, commission, ramp, and deliver you a battery grade product by 2025. Not if you cut me the check today. So there isn't enough add-on expansion that you could do with existing assets that you could meet the needs of if EVs explode.
So how do you see this playing out? Because lithium is not rare. There's no shortage of lithium. But is it the fact that these companies are not ramping production now? And is that also due to there being a current oversupply where they're trying to feed that oversupply through the system?
Yeah, so, and that's a good point. So here's the thing. So the price in China in the spot market is low. The price, the import market into Japan and Korea to the tier 1 battery cell manufacturers that put those cells and deliver those into your VWs, your even Teslas, that's where Sumitomo, shipping with Panasonic.
Question on that. So when you talk about the spot price of lithium, what exactly are you referring to there? Is that, say, lithium hydroxide, the lithium carbonate?
So it's both. So this is the thing that's the sort of the nuances of the lithium world. Historically, people like Albemarle, and Albemarle is the biggest producer of lithium, they would not build and develop and expand their production unless somebody downstream guaranteed them a price, a contract price that said, if you build this, you're going to make your 15 to 20% after-tax IRR, whatever the number is. They work roughly on 2 times WACC, weighted average cost of capital. That's roughly what they work off. So historically, Albemarle did its expansion on the basis that someone would pay them $10 or $12 or $14,000 a ton for their lithium. And that's how the industry went along. The latest boom that we've had is you've had newcomers come in, and you've had the rise in a separate market. So for a while, you had those very distinct contract markets, and then suddenly EVs took off in China, if you remember, in 2016 and 17, and the price exploded, and suddenly there was a market outside of the contract market that had been very small. And suddenly now a lot of independent converters popped up in China, high net worth people, deciding to get into the business. In other words, not the incumbent industry producers. That was an oligopoly, effectively. So as more and more of those people pop up, and the less, the excess production over and above what's delivered into the contract market has meant that there's been a spot price rise. Okay. Now, Japan and Korea have no domestic production. And like other commodities, they are paranoid about not getting the quality and what they need and consistency, because they do not have, outside of their suppliers, they cannot sort of threaten or have recourse to or have the opportunity to get someone else deliver into that, to their needs. China, of course, there's masses of production capacity there, so that's a market unto itself. So in the boom of 2016 and 17, there was the price was trading way in excess of the marginal cost of production. I mean, it hit a high of $25,000 a ton, and the marginal cost of production is somewhere between 10 and 12,000.
Okay, I just
want to... again, as I said to these guys, they get permits, they can construct quickly, they built up capacity, and now we're having the hangover of the very high prices of 2017. And it's something I think for your listeners to think about is like all commodities and specialty chemicals, a price spike is the kiss of death. You have a price spike in a commodity, and people are going to look to thrift it out of whatever it's used for. They're going to look at alternatives, and a lot of marginal projects will get financed and green lighted when, literally turkeys can fly in a hurricane, basically. So if you look at the example, why do you think people are pushing? It's not just the DRC being the central supplier of cobalt. Cobalt hit $110,000 a ton in 2017, and nickel is 12 or 13. So what you've seen is the change from nickel, manganese, cobalt being 111 equal parts in the battery to now people striving to do 8 parts nickel, 1 part manganese, and 1 part cobalt. And it's not just the DRC, it's also, you can't cope with prices at that level. So again, the kiss of death, and it's caused the transition towards, there's energy density issues and all sorts of things, but also the price drove it.
Okay, that brings up an interesting point, and I just want to go back one step. So we were talking about both lithium hydroxide and lithium carbonate. I just wanted you to maybe briefly discuss the difference, because what I've seen at the moment is lithium hydroxide's used more for the high nickel cathode chemistries, while the carbonate's used more for, say, the lithium ion phosphate that are more predominantly used in China.
Yes. So what the issue with a good way to describe the differential. So in the sintering process, the problem is with a high nickel cathode. I think there's a debate, but let's call it when the nickel represents more than 65%. That's the sort of threshold. The temperatures in which you need to rise to in order for the lithium carbonate to go through the sintering the cathode sintering process is high, and it can damage the crystal structure of the cathode. Whereas if you use lithium hydroxide, it's a lower temperature and quicker, and it doesn't cause the damage. So it results in a better performance of the battery for the high nickel. So when you look at industrial uses for either carbonate or hydroxide, of all of those things, so it's some organic, some inorganic, 80% of those use carbonate. So we're talking about glass, ceramics, all of those things. That's a carbonate-based business where you use lithium hydroxide and you use technical grade for grease, but that's only about 20% of that market. Then when you look, so to be clear, you can use lithium hydroxide in any cathode. It's a question of cost. So even up to, and I've seen some commentators are estimating a very high proportion of 622 batteries, so 60% nickel, 20 cobalt, and 20 manganese as being hydroxide, but it is an agnostic cathode. You can use either, but the argument is you get a slightly better performance with hydroxide, but it does come down to costs. Above 65% nickel, you cannot use carbonate. Again, as I mentioned, the issue is around the temperatures required for the sintering, which can damage the crystal structure. So your NCA, like what Tesla uses, I think that's about 85% nickel or what have you. That's absolutely and only hydroxide. Okay,
and is that one of the reasons that we've seen a growth in lithium hydroxide over the last 5 years?
So if you look at the tier 1 battery, the cell makers, and what VW and so on have required, they are paranoid about the provenance of the cobalt in their batteries. So if you can thrift down the amount of cobalt in the battery, then the chances are you can secure it from, let's just call it something that you can blockchain, or exactly where it's come from. And then also the risk, I guess, because it's not so much, yes, the DRC is an issue, but it's also a very small number of players control the cobalt market. So you are always at risk of a price spike again. And let's be honest, I mean, what is one of the biggest hurdles other than charging and charging infrastructure and speed of charging and so on and range is the cost of the battery. The biggest issue and the biggest concern that OEMs have had is how do I get my electric vehicle to compete against the internal combustion engine equivalent and be cheaper as a sticker price and be cheaper on full life cycle, including charging. And that hinges largely, I mean, batteries, everything. So looking at that, I think they decided nickel, nickel sulfate maybe a little more, but let's nickel call it $12,000 a ton. Cobalt is 3 times that even now, but it has been, nearly 10 times. Nickel is a well-established market. There are alternatives to it. It has a futures market. So putting that into the battery from a price risk perspective, it was positive for them, I think, in terms of getting the prices down. And then the next thing, of course, is energy density. There are some safety issues, but the energy density is improved with high nickel cathodes. The LFP, as you've seen now, this whole thing with the blade, and Tesla are going to use LFP in their short range Model 3 in China. What they did is they managed to, if you look at the energy density at the cell level and then the energy density at the pack level, there's quite a loss with NMC. So what LFP has managed to do is go from cell to pack. So the differential in energy density has narrowed, and that's made it more competitive at the pack level versus NMC. NMC at the pack level is still very high. Some of the CATL ones are nudging 300 now, watt-hours per kilo, which is very high. But at the pack level, it's lower. So that is why you're seeing that it's from a cost and a density perspective, LFP has had a boost with this. But my understanding is that the cell-to-pack technology, that improvement is it's not far away where that will be applicable to high nickel cathodes as well.
Okay.
So I think to say that they're not going to have the evolution of battery tech is going to be an ongoing process, and I expect that the NMC, high nickel cathodes will also have some improvement from cell to pack as well. Who knows? Maybe Tesla's going to tell us that in the next couple of weeks.
Oh yeah, with Battery Day, I guess.
So it's not just range; it's also, it's also trying to lose less energy between, a cell to module to pack, seeing if you can reconfigure it in a better way.
Okay. And who are Tesla's suppliers for lithium?
So they have signed quite a lot of contracts, but again, we'll get to the disappointments of these things. But Albemarle and Livent, I think, flow through into their supply chain, and I'm sure at some point in time, Ganfeng will as well. And those three pretty much dominate and cover the market. So in Japan and South Korea, which, as I said, is where tier 1 batteries are made. So what you and I, consider the Western OEM car manufacturers, 80% of their hydroxide requirements come from China. Now, Albemarle and Livent both own conversion facilities there. In Livent's case, they reprocess carbonate that's come from Argentina from their project. But the point being, the hydroxide that ends up in those batteries is shipped from China, 80%, and that percentage is rising.
So let's just stop there for a second. Like, if we were to map it out, so you would mine the initial, say, spodumene from Australia, ship that to China, have it converted. From China, then you would send it to the US.
You would send it. No. So let's say take a Tesla. So let's just say it comes from Albemarle's plant. So Greenbushes, Aussie, it gets shipped from Bunbury, I think, through to China. And then it gets converted into lithium hydroxide in China. Bear in mind, it has to be trucked from port to converter, from converter back to port, then to Japan, to Sumitomo, who then does the cathode. They ship the cathode then to Panasonic. Then it gets put in a cell there and in a pack and into a Tesla. Then that Tesla gets shipped to wherever it's getting sold.
Wow.
So this is why, from a carbon footprint and from a sustainability perspective, consumers and especially Europe are wanting for the supply chain to be simplified and localized. Because the truth of the matter is, if you think about it, and it is something that needs to be addressed, at the moment, I'm sure you're aware of the CO2 emission penalties that that's implemented this year in Europe. But the thing is, what they penalize is how much CO2 emissions you have per kilometer traveled. But they don't, so that if your car pollutes from the showroom floor onwards, you're penalized. But there is no audit or assessment of what it took to get that car on the showroom floor, that EV. It doesn't differentiate if your lithium chemicals are made in a coal-driven fire plant in the middle of wherever, or it is, or if it's in a green energy, process. So that's why the interesting difference, and it'll be interesting to see where things go. So VW has said they prefer the hard rock route, but a brine producer will say to you, from a carbon footprint perspective, the wind and the sun evaporates and improves the grade of the lithium. It doesn't go through a kiln at 1150 degrees. The issue around brines is the sustainability issue. Is it impacting the environment around it? But from an energy usage perspective, it's less than something getting mined, trucked, shipped, and then put through a kiln.
So the lithium carbonate then that would be used, say, at the China Gigafactory, would that be the exact same process, only you're shipping the brine from South America to China and then going through?
So you'll be shipping the carbonate. So the carbonate is made in, these days SQM is struggling to make a battery-grade carbonate, even having done it. But yes, so you can still make carbonate from hard rock. So it can come from Australia, be processed. They are going to be using CATL, so you would need to look back through CATL's supply chain to see where where their suppliers. They are looking. They have a 15% stake in a company called Yimin Tianyi that's looking to set up its own conversion plants. So some hydroxide and some carbonate. So they are looking to take material, hard rock spodumene concentrate from Australia and processing it in China.
So one final question for you. People have been talking about sodium batteries as the future. What are your thoughts on that?
So I won't speak specifically to sodium, but I'll just talk in general. The thing you've got to realize, as I mentioned before, is lithium-ion batteries are a 30-year overnight success. It's taken a lot of refining to get to it. So my question to you is this. How many Elon Musks come around in every generation, would you say? Let's just say maybe a handful.
Yep.
How many Elon Musks come around that run a $140 billion market cap company? Not too many. We're probably down to just him. He has the access and the balance sheet to adopt any technology. I mean, if something has merit, he can shift in that direction. The problem that you have is every couple of years, there's guys in a lab coat somewhere who've got $1 million to $2 million grant, and at the lab scale, create something phenomenal. It can produce watt hours that is double everything that's out here now, do all sorts of things. The problem that you have is to take something from lab scale to then bench scale and then commercial scale, where you can produce it in high volume and you can produce it at a decent cost. The options start to thin out. So it's not to say that something won't come along and change everything, but I think there's a very sound reason why Elon Musk and others have gone the lithium-ion route. And what we've seen is if you look at the future evolution of battery tech under lithium-ion batteries, the next state is solid state. Solid, metal anodes and so on, where you're going to get, 500, 600, 700 watt hours per kilo. It's going to double whatever we've got now, and hopefully at a reasonable cost. You have an established technology and battery tech that can take you to the point that it's far superior than internal combustion engines. If you want to go and chase in another route, I'm not saying it can't be done. I'm just saying to you, practically speaking, some of the brightest minds in the world have looked at this and have gone the lithium-ion route. So can other technologies evolve and do it? I would say if there's merit with something at the lab scale and then the bench scale, someone like Elon Musk could pivot and buy everything that he needs to buy with the balance sheet that he has to harvest that improvement. But for now, lithium ion, where it's at now with high nickel cathode, LFP, blade, etc., and pivoting and going into solid state batteries the runway is there. Everything that you need is there.
Okay.
And also to re-gear cell plants to open up for different technologies, I'm not sure. So I'm not saying no, I'm just saying to you, there's always a guy in a lab somewhere who's coming up with something brilliant, but taking it from there to actually disrupting the industry is a big ask.
Yeah, we see that almost on a weekly basis, the new battery breakthrough. All right, well, thanks again, Rodney, and I guess we'll talk very soon.
Excellent. Keep well.
So I hope you guys enjoyed that episode. A lot more supply chain episodes coming up soon. As always, a huge thank you to the Patreons that support the show, and a huge shout out to Winston. So till next time, I'll see you guys soon.